If you use an unstructured mesh generator to generate your meshes for CFD, you may have wondered what's going on behind the scenes after you click the Generate Mesh button. You may have also found that the unstructured mesh generator raises some warnings or errors telling you that stair-stepping is being used or that poor quality cells are being generated somewhere in your unstructured mesh. What I'm going to do in this talk is actually go through the general process of how an unstructured mesh generates a mesh, and you could be able to use this understanding to help diagnose why poor quality cells may be generated in your mesh and to understand what's going on with stair-stepping and why that's being created in your particular mesh. You're going to be able to use this understanding to then improve the quality of your meshes that you generate because you're actually going to understand what's going on behind the scenes. Right, if you're looking forward to this talk, sit back, take some notes, and let's get into the talk. The background for this talk is that it's really useful to have a good general understanding of how unstructured meshes are generated. The reason it's good to have this understanding is that when you use an unstructured mesh generator and the mesh generator produces some poor quality cells or some errors, this will enable you to be able to diagnose and find why those poor quality cells are being generated, and then to be able to have a better idea of how to fix the mesh. And before jumping into the talk, I just wanted to emphasize that I'm not going to be going through specific meshing algorithms here. So I'm not going to be showing you exactly how a particular mesh generator generates an unstructured mesh, but I'm going to be giving you some qualitative understanding so you can see the process for how cells are assembled into an unstructured mesh. And the other caveat I wanted to make is that many modern mesh generators have the capability to use polyhedral cells, so that's cells with many different numbers of flat faces, and you can see an example there on the slide of what a polyhedral cell might look like. And I'm not going to be covering polyhedral cells and polyhedral transitions in this talk. I'm only going to be covering traditional cell types such as hexahedras, tetrahedras, prisms, wedges, and pyramids. So let's start with inflation layers, or sometimes called prism layers. Generally, how you can think of an unstructured mesh generator as working is the first stage is the unstructured mesh will generate a surface mesh on all of the cells that cover the CFD domain that you want to generate a mesh. So all of the bounding surfaces, a surface mesh will be generated for those surfaces. And sometimes as a user, you have some degree of control over the surface mesh. You may be able to have some input yourself into how that's generated. And in other mesh generators, the surface mesh will just be generated automatically. The second stage that the mesh generator will often do is take that surface mesh, and for the specific surfaces that request inflation layers, the mesh generator will project that surface mesh normal to the surface into the volume and create a set of inflation layers. And the layers are often called inflation layers because they grow and they get larger, or they inflate as you move away from the surface. And so a typical set of inflation layers may look something like this. And the first problem that often arises, and is probably the main reason why poor quality cells are generated by unstructured mesh generators, is when the layers aren't projected exactly normal to the surface. And when the layers are projected at some angle, then this can lead to the small thin cells that are very close to the wall being generated with some skewness or some tilt to them, which ultimately ends up raising warnings, whether they be non-orthogonality and skewness. And the reason that layers may be projected away from the surface at some angle could be due to proximity with other surfaces. You may have sharp corners, or you may have layers from other components nearby. So generally, if you're seeing this and your layers are being generated at an angle to the wall, have a look at the geometry and actually have a look at the mesh yourself and try and work out why are the layers being projected normal at an angle to the surface, because this is probably what's ultimately resulting in poor quality cells if they're the ones close to the wall. So that's very simple, and that's a very easy way to understand how some basic poor quality cells can be generated by an unstructured mesh generator. But how else can poor quality cells be generated? What other problems could arise that you need to be looking for when you're generating an unstructured mesh and constructing your geometry? What I want you to think about is the next stage. So after the inflation layers are generated, what then happens is the mesh generator will need to fill the remaining space with cells. And this region is often called the volume mesh because it's a large volume of space and the mesh generator needs to fill that space with cells. And this volume mesh may be hexahedral based, it may be a hex core, it may be filled with tetrahedral cells of some type, or it may be filled with polyhedral cells. And what the mesh generator needs to do is it needs to fill the space with these cells, but it also needs to transition from the layers that we've just generated out to the volume mesh. And that's really going to be the focus of this talk, is that transition between the inflation layers and the volume mesh. And the key to understanding this process for how the mesh generator is going to transition between the layers and the volume mesh is the top surface of the layers, which I've highlighted in blue here on the slide. And this surface is sometimes called the top cap. You'll see it referred to as the top cap in some mesh generators. And in other mesh generators, it may not be mentioned at all. But I'm going to refer to it as the top cap. It's this surface. And the key to understanding is that new cells are going to be grown from the top cap out into the volume. And you can see these cells highlighted in purple there. And it's the growth of these cells into the volume that's ultimately going to allow us to transition from the layers into the volume mesh. And I just wanted to make a small side point here that, of course, mesh generators may not actually generate the cells in this order. They may use different algorithms for creating layers and the transition and things. And I'm not going to be covering those today, but this approach is just useful for your understanding, for looking at a mesh and understanding where the cells come from and why they're there. So we've grown the layers, and then on top of the layers, starting from the top cap surface in blue, we're going to be growing new cells off the top of the layers. And the key to understanding this is to think that square cells in that top cap surface are going to be grown upwards into pyramids, whereas triangular cells are going to be grown upwards into tetrahedral cells. And the difference between a pyramid cell and a tetrahedral cell are the number of faces and the shape of the faces. But for our understanding, the primary difference here is that a square cell becomes a pyramid, a triangular cell becomes a tetrahedra. And the same process is being followed. Those faces are being grown upwards into 3D cells. And of course, when we do that and we grow pyramids and tetrahedra from the top cap, there are going to be some gaps between those cells. And what the mesh generator will do is fill in those gaps. And an easy way to do that is to use upside down pyramids and upside down tetrahedral cells to fill the gaps between the pyramids and also between the pyramid faces and the wall, for example. So you don't need to know exactly how that's done, but just for a general understanding, we're going to be growing those pyramids and tetrahedra and then using upside down pyramids and tetrahedra to fill in the gaps between the cells. And understanding this process has some useful implications for us, and it's going to help us to ultimately create better quality meshes when we really think about this process. The first thing I want you to do is to think about the surface of that top cap. And if those 2D cells in the top cap have a very high aspect ratio, so for some reason if you had very long, thin quadrilaterals, the quadrilaterals, of course, become the base of the pyramids, and the pyramids are grown upwards from these quadrilaterals. So if we have a high aspect ratio top cap, then the pyramids themselves are going to be very thin. And these pyramids, of course, don't have very high quality. As you can even see just from the triangular faces there of the pyramids, they've got very acute angles. So these pyramids aren't going to have very high quality. And this means that our top cap, we're going to need to be careful with how we generate the top cap of the layers. And of course, it also follows that if our top cap has very skewed cells, so if our cells aren't very close to regular squares or equilateral triangles, then that face, of course, once again becomes the base of the pyramid. And when we grow a pyramid or a tetrahedra up from that face, you can see that the resulting pyramid is going to have very poor quality. So this general understanding is really telling us that we want a good quality top cap mesh. And this is probably not something you've thought about before. The top cap mesh is having implications for the tetrahedra and the pyramids that are grown from it. So the top cap mesh, how would you look at this in a mesh generator? Some mesh generators may not even give you the option of selecting or looking at the top cap itself. And for these meshes, what you can do, and when you're going to be generating your mesh, you can think of the top cap as a projection of the surface mesh. And to a certain extent, this is true because we're starting with the surface mesh and then we're projecting up into the volume to generate the layers, and then the top surface will become the top cap. So the quality of the surface mesh is ultimately what's going to be determining the quality of the top cap, as well, of course, as the angle that those layers are projected off the surface. And this is why the surface mesh quality is going to be important. And I just wanted to make a small side point here that, of course, the top cap is not going to be an exact projection of the surface mesh because the layers aren't always grown normal to the wall. Sometimes they're grown at an angle, and we have other surfaces which may be connected together, and so the layers may be projected at some angle and they may be enlarged or shrunk. But generally, for our understanding, and when we're setting up our geometry and creating our surface mesh, you can think that the surface mesh you create is going to be approximately projected upwards to become the top cap, and that's where you're going to generate your pyramids and your layers from. And so what does this mean? Well, it means that when you generate a surface mesh, the quality of those 2D cells, the squares and the triangles that make up the surface mesh, don't directly affect the quality of the CFD solution. But those 2D cells are going to be projected upwards, first to create layers, then to create a top cap, then to create pyramids and tetrahedrals. And the quality of those 3D cells are ultimately going to be affected by the quality of the 2D surface mesh. And this is why it's important to have a good quality surface mesh. If you're generating some poor quality layers, for example, or pyramids above the layers, then a good idea for you to do is also just have a quick look at your surface mesh. Is your surface mesh, is it really bunched together, or have you got some skewed cells on the surface? Because that can tell you why the unstructured mesh generator is then generating those poor quality cells. And what this is really telling us is that when we generate a surface mesh for an unstructured CFD mesh, what we want to be aiming for is a surface mesh that uses equilateral triangles and perfect squares. They're going to be the ideal cell type for our surface mesh because as they're grown upwards, these are going to become, you can think of these as the base, firstly of the pyramids for the square cells, or the base of the tetrahedra for the triangular cells. So you're implicitly creating the base of those transition cells when you create your surface mesh. So we know what kind of shape we want. We don't want high aspect ratio, we don't want skewed, we want something close to equilateral perfect shapes. But how big should the surface mesh be? This is probably something else you may not have thought about before. How large should these cells in the surface mesh be? Well, the key is to actually think about the volume mesh that you're going to be generating above the layers and the transition cells. And I've got 3 examples for you here on the slide. The first one is a very fine volume mesh, the second one is a medium, and then the third one is a very coarse volume mesh. And of course, you as the user will often have some degree of control over the volume mesh that the unstructured mesh is going to try and generate. This one over here, for example, you may have specified cells which have dimensions of 10 millimeters, whether they be hexacore or tetrahedral. These cells here may be 20 millimeters and these cells here may be 100 millimeters. And without actually going into any detail and understanding how the mesh generator is going to transition from those pyramids out to the volume mesh, it's going to have to make the transition somehow. It's going to have to join things up and connect those cells together with edges and vertices. And just by looking at it, without even going into the algorithm, you can see that the transition for this mesh is going to be quite challenging because somehow those pyramids are going to have to all be pulled together, generating very thin tetrahedra or pyramids to try and match up with the volume mesh. And likewise over here, those pyramids are probably going to have to expand out quite a lot in order to match the edges together on the volume mesh. And so without actually understanding how this transition process works, this is telling us that it's a really good idea to try and match the size of the surface cells to the size of the volume cells, because this is going to make the transition easier for the mesh generator, and ultimately the quality of the cells is going to be much better. So what does this mean? Well, it means when you're thinking about the parameters for your mesh and how you're going to set up the unstructured mesh, so before you press go on the mesh generator, the controls that you put in for the cell size, you may have thought about how large you want your cells to be in the free stream, in the free volume, and it's a good idea to try to match this size to the surface mesh size, or at least be fairly close. So 50 millimeters and 40 millimeters would probably work fine, but if you had 50 millimeters and 5 millimeters, that might cause some difficulty for the mesh generator. And indeed, I also wanted to make a small side note here that some mesh generators, which will just generate your entire mesh for you, including the surface mesh, will actually be doing this implicitly under the hood. So you won't see it, but when you press run, the mesh generator will look at the size of your volume mesh and then try and create a surface mesh that has a similar size to the volume mesh, so that ultimately the transition will be better. But if you have a more manual mesh generator and you can actually create the surface mesh yourself, have a think, how large are those cells going to be away from the surface, or at least close to the surface, and try and get your surface mesh to be a close size to those cells. And then, of course, you then want to be aiming for close to square cells and equilateral triangles in your surface mesh. And there are some other interesting implications of this as well. We can really run with this idea and really understand lots of implications for our meshing process. Some of you, when you generate surface meshes, may be used to generating graded surface meshes, where the size of the squares or the triangles gets a lot smaller. Say when you're close to a boundary or another surface, you may grade the surface mesh to give you a surface mesh which may look something like this. And while a surface mesh like this may be very good for a structured mesh generator, for an unstructured mesh generator, this is really not going to be what we want to do. And you can see straight away the reason for that is the surface mesh is then going to become the top cap, and these squares, these quadrilaterals, ultimately become the base of the pyramids. So while the pyramid here in the bottom left and the pyramid here in the top right are probably going to have good quality, they've got a square base, you can see that these surface cells over here in the bottom right and the top left corner, they're going to generate really poor quality pyramids as well. So this is something to bear in mind. When you're committing to using an unstructured mesh generator, you really want to be going for that equilateral surface mesh with a good spread of cells that have similar sizes. And here's a really useful example to indicate the implications of this. I want you to consider just a simple mesh of a pipe or a cylinder, as you can see. And for those of you who've done block structured meshes before, you may be used to generating meshes which look something like this, where you have some kind of O-grid structure or block structure on the ends of the cylinder, and then the cells are projected along the length, and we can stretch out the cells towards the middle to reduce the cell count. And this is fairly typical of what you would do in a block structured mesh. However, when you're now thinking in terms of an unstructured mesh, this would be a really poor quality surface mesh to use if you wanted to grow layers and then pyramids and transition into an unstructured mesh in the free stream. Because of course, the surface cells, these are going to become the base of your pyramids and tetrahedrals, and you can see they've got high aspect ratio, which is not what you want. So actually, if you were meshing the same flow scenario, a pipe flow, but with an unstructured mesh, you'd want your surface mesh to look something more like this. And you can see for the entire surface, we've got squares and triangles that have similar size, they're close to equilateral, and so they're going to generate very good quality layers and then pyramids when they're projected off the surface. And of course, some of you will notice that unfortunately this approach does lead to a higher cell count, because each one of these equilateral cells is projected off the surface to create a set of layers, and so actually the total number of cells is probably going to be far higher than the block structured mesh that we used here. So that is one of the downsides of this approach, but it will ultimately lead to a higher quality mesh if you're using an unstructured mesh generator. Now I want to take a small detour and think about structured and swept regions. So many of you who use unstructured mesh generators may be used to having the bulk of your mesh as unstructured with layers on some surfaces, but sometimes you have small regions of structured mesh within your unstructured mesh. And this is typically used to represent porous regions and porous zones. They're typically represented with small blocks of structured mesh within an unstructured mesh, or solid components if you're doing a conjugate heat transfer simulation. So you may have regions of structured mesh within your unstructured mesh. And the key point of understanding here, which follows from everything we've talked about before, is of course at that transition between the structured mesh into the unstructured mesh, the mesh generator is going to have to connect the meshes together, and the way it will do this is once again grow pyramids and tetrahedra from the surface of the structured or swept mesh region. So this is the point of understanding here, is it's not just from the bounding surfaces of the CFD domain with the walls, it's also from the surfaces of structured meshes that may be floating within your mesh somewhere. We're also going to be generating pyramids and tetrahedra there. And so the same set of recommendations that we've been following throughout this talk also apply for the structured and the swept mesh regions. If you think of the top surface of your structured region, of course we're going to be generating pyramids from there, and so we also want to have a good quality surface mesh for the structured region as well, because ultimately that forms the base of the pyramids. So here's the other point of understanding for you, is that when you're generating those structured regions, you also need a high quality surface mesh for these components, as well as the walls and the boundaries of your domain. But there's another subtlety here, which some of you may have missed, and I really wanted to highlight in this talk. With a structured or a swept region, of course, we also need to generate pyramids and tetrahedra from the sides of the region as well. So when we have a wall, a normal wall surface, and we're growing inflation layers, and then we grow pyramids over the top, we're only growing pyramids from the top surface. But of course, when we have a floating structured or swept mesh region within our mesh, we have to grow pyramids and tetrahedra from all of the surfaces of that region, because all of the surfaces need to transition out into a volume mesh. And so this has really important implications for our structured or swept region, because in some scenarios, you may want to use many different layers through the thickness of your structured region, which may look something like this. But of course, the cells on the sides, because they also need to be grown into pyramids, if you use a lot of thin layers through a porous zone or a structured region, they're also going to result in bad quality pyramids. And this is where a really interesting compromise arises, and is one of the key points I wanted to get to in this talk, is that if you do have a porous region in your mesh that you're representing with a region of structured mesh, of course a swept mesh approach is really good here, because all of the cells are going to be aligned with the intended flow direction and the pressure drop that's going to be applied by the porous zone. But there's a balance here, because if we use very thin cells through the thickness of our porous zone, what that's going to be doing is spreading the pressure drop or the force from that porous zone out over more cells. We're spreading the force out, which is ultimately going to be resulting in a more stable calculation for the CFD code, because rather than applying a concentrated force to one or two cells, it's spread out over multiple cells. But then of course, if the cells are too thin, the pyramids that we grow off the sides of the porous region could have poor quality. So there's definitely a compromise here, and the way to do it when you're creating your own structured and swept mesh regions is actually have a look for yourself. Look at the mesh, look at the sides, and look at the pyramids. Are those pyramids, do they have poor quality? Is the mesh generator complaining about them? Is it giving errors? Or if it's not, does it look okay? And how many layers have you actually got through the thickness? One cell is probably not enough. You're not going to get enough resolution there. It's going to be quite unstable for the CFD calculation. Maybe you want a few more. And so this is where some experience comes in, and you'll actually have to look and make some engineering judgment for yourself. And the final point I wanted to go with in this talk is stair-stepping, and this follows directly from what we were thinking about with the regions of structured mesh. What I want you to think about is, once again, generating those inflation layers normal to a surface in the CFD domain. We're projecting those layers off from the surface, but for some reason, what if we stop the layers before a wall? What if we only create inflation layers on part of our surface? So maybe our surface is split into two, and we're only going to project inflation layers off one part of the surface. Well, of course, what's going to happen is the sides of the inflation layers are going to be exposed. And what's the mesh generator going to do in this case? Well, we've got faces, and these are going to need to be connected to the rest of the volume mesh. And so what the CFD code might try and do is to grow pyramids, again from the sides of the layers. So the same way that pyramids will be generated from the sides of your structured and swept mesh regions, if the layers don't cover an entire surface, then the mesh generator may try and grow pyramids from the sides of these layers. But of course, this is a really big problem, because typically with layers, those very first few cells are going to be really thin. These quadrilaterals for the first few layers are going to be really thin, and the pyramids would have terrible quality if we generated them there. So what can we do? A very popular approach that many mesh generators will use is something called stair-stepping. And what does stair-stepping physically mean? Well, what stair-stepping physically means is creating a wedge cell, or a triangular prism, as you can see here, and slotting the wedge in on the end of those exposed inflation layers. And what's the difference between a wedge and a pyramid? Both a wedge and a pyramid have a quadrilateral base, but the difference is a pyramid is drawn together at a point at the top, whereas the wedge, you can see the triangular faces are grown up towards an edge there. So a wedge is slightly different to a pyramid. And we can slot wedges in on the ends of those exposed inflation layers. And what that then allows us to do is, rather than growing pyramids from the ends of the inflation layers, we can grow pyramids from the top face of the wedge, as you can see here. And the top face of the wedge is actually a pretty good square face, so we can grow a really good quality pyramid from the end of that wedge, as you see there. And this process of gradually covering up the ends of those exposed inflation layers is called stair-stepping, and it's a really good way to avoid us putting pyramids on the ends of the layers. And often, if you're using an unstructured mesh generator, of course, you may not request stair-stepping yourself directly. You're not going to tell the mesh generator, I would like you to use stair-stepping. Often you'll click the mesh generator button, and then what will happen is maybe warnings or error messages will come up saying that the mesh generator has used stair-stepping at some locations in the mesh. And why does that happen? Well, there are a number of possible reasons, and ultimately you need to have a look at your mesh and try and work out why. But some common reasons why stair-stepping will be used. The first one is if you have a single surface that has requested layers over all the surface, but you may have broken it up into different sections and requested different numbers of layers on the same surface. This same thing can also happen if you have a corner. If you're going around a corner in the domain, it's still a continuous surface, but if you request a different number of layers on one part, say 4, and then 3 layers on the other part, the only way to transition between those layers without having that exposed quadrilateral face for generating a pyramid is to use a wedge and to slot a wedge in there. So that's a really common way that stair-stepping will be used. Another common way is if there's a physical object or boundary that the layers are in danger of crashing into. We don't want that, we want to preserve the layers. So some mesh generators will use stair-stepping and will shave off some of those layers just locally so we can get around the object and then add them back in again. That's a common way of using stair-stepping. Other mesh generators may just compress the layers locally, squeeze them all together to get under the object. And the final one, which I haven't got an image for you here, is a common mistake where if you have your layers and you haven't run them all the way into the wall, but there's a gap where you just stop the layers on the surface, that of course is going to leave loads of exposed faces, and the mesh generator will add wedges to cover off those exposed ends of the inflation layers. So just a quick summary of what I've talked about today, and the main point of understanding here is that pyramids and tetrahedral cells are grown from the top cap, that's the top surface of the inflation layers. And for good quality pyramids, what we want is we want the base of that pyramid to either have an equilateral triangle or a perfect square, because that's going to allow us to generate a good quality pyramid. And we also want the size of those surface cells to be close to the size of the volume mesh, so that when we get to the top cap and those pyramid cells, the transition into the eventual volume mesh is going to be a lot easier for the mesh generator. And the other point of understanding here with pyramids is that pyramids are going to be grown from the sides of structured regions. So if you have a porous zone or a region of swept mesh, pyramids are going to be grown from all of the surfaces of that domain. And once again, we need to make sure that the sides of those structured regions aren't thin and that they don't have poor quality, because that's ultimately going to result in a poor quality pyramid. And the final point is that many mesh generators will use stair-stepping or wedge cells, or triangular prisms as they're sometimes called, to cover the exposed ends of inflation layers to block pyramid growth from the ends of inflation layers, and instead grow the pyramids from the top of the wedges, which ultimately will result in a higher quality unstructured mesh. So that brings me to the end of the talk. What I'd really recommend you do now is, if you have an unstructured mesh yourself, open up your mesh generator and drop a cut plane through your unstructured mesh and actually have a look at the structure of the mesh you've got there. Can you see the inflation layers? Can you see the pyramids and those tetrahedral cells on the top of the layers? Is there any stair-stepping? Can you see where stair-stepping might happen? And if you have any structured regions, also have a look, and can you spot the transition around the structured region? I'm really hoping that with this talk, you're actually going to be able to look at your meshes with new eyes now and actually understand what's going on behind them. And if you found this talk useful, of course, let me know in the comment section. I really enjoy hearing from you and hearing your messages. And let me know, would you like more talks in this style? Do you like understanding how mesh generators actually work? Because if you do, I might consider putting together a few more talks like this in the future. And thank you all very much for watching, and I'll see you in the next video.